Abhiyanta Siksha is launched with a motto to impart an experiential understanding of technical education. The course outcomes are: equips junior engineers to solve real-time industry problems, prepares graduates for competitive exams, supports engineering students in their graduation studies, benefits diploma and high school students in engineering sciences. Problems are explained, solved, and supplemented with hands-on practice for students. Welcome to the online course Abhiyanta Siksha. The topic that we are covering in this course is engineering mechanics with subtopic friction. The contents of this course is categorized under Session 1 and Session 2. Under Session 1, Introduction to Friction, Definition, Types of Friction, Mechanism of Friction, Laws of Friction, Values of Coefficient of Friction, Friction Angles, Types of Friction Problems, Practice Problems under Static Condition, Practice Problems under Dynamic Condition. Under Session 2, Applications of friction such as wedges, connected bodies, ladder, belt friction, rolling wheels. References for this course material are given here. Majorly J.L. Merriam, L.G. Craig, Engineering Mechanics Statics, similarly Engineering Mechanics Dynamics. Beer and Johnson, Vector Mechanics for Engineers, Statics and Dynamics. F.L. Singer, Engineering Mechanics, Statics and Dynamics. Irving H. Shames, G. Krishna Mohan Rao, Engineering Mechanics, Statics and Dynamics. So, Session 1, Introduction to Friction. Since it comes under engineering mechanics, let's just recall what is engineering mechanics. Engineering mechanics is a branch of physical sciences that is concerned with the state of rest or motion of bodies subjected to the action of forces. It is broadly classified into statics and dynamics. Let's start with the definition of friction. Friction is defined as the contact resistance exerted by one body upon a second body when the second body moves or tends to move past the first body. In other words, friction is a retarding force always acting opposite to the motion or tendency to move. Let's understand this phenomenon of friction from these diagrams. Let this be a ground surface and this be a block resting on the ground surface. When the block is pulled with certain amount of force in right direction, frictional resistance force occurs at the contact surface between the block and the ground. The red color surface which is occurring between the block and the ground is said to be frictional surface. This resistance force is represented in opposite direction to the pulling force. Let's understand this through the schematic sketch. If this is the block of weight W, the weight vector is always represented towards the gravity direction and perpendicular to the ground surface. Now, N is the normal reaction occurred by the ground onto the body, and this vector is opposite to the weight W. Now, if P is the pulling force that is exerted on the body, then F is the frictional resistance force that acts opposite to the pulling force P. Now, let R be the resultant vector of N and F, which is subjected at an angle of phi. Let's get into the details of these friction parameters in the next slides. Is friction boon or bane? Let's understand as a bane. In certain machines, the goal is to minimize the retarding effect of friction forces. That means here the friction that occurs should be reduced to have maximum efficiency of the machines. So, the bearings of all types, you can see these ball bearings where the friction occurs on the ball surface, which are held between the inner race and the outer race of the bearing. If the friction is not reduced, then wear and tear of bearings occurs faster. Hence, a lubrication is used in order to reduce the friction. The effort is to minimize the frictional forces. Next example is power screws. The power screw rolls inside the nut and the frictional forces occur in between the nut and the screw. So, it is necessary to minimize these frictional forces to get maximum efficiency of the screws. Another example is the frictional force that exists between the gear teeth. The teeth rolls and slides one over the other, and friction does happen while driving. It is necessary to minimize these frictional forces to maximize the efficiency of the system. Similarly, the fluid friction occurs inside the pipeline, and the fluid friction occurs on the outer surface of the aircraft, which can increase the drag effect on the flights. So, these are some of the examples for friction as a bane. Let's look at friction as a boon. In certain machines, the goal is to maximize the retarding effect of the friction forces. This is an example of belt and pulley. In this particular system, friction in fact is the driving force for the belt to roll on the pulley. So, it is important that friction exists and is maximized to get a better efficiency. Then comes your wedges. Basically, wedges are used to lift the bodies. And here the friction again is a driving force for the function of these wedges. Hence, the frictional force has to be maximized for the better efficiency of the machine. A human being walking on the road requires friction. You just can't imagine to walk on a road or run on a road without friction between the shoes and the road. Similarly, a tire of the car rolls on the road with the help of friction. So, in certain cases, friction is a boon for the system. Now let's look at the types of friction. They are classified as dry friction and fluid friction. Dry friction develops when the unlubricated surface of two solids are in contact under a condition of sliding or tendency to slide. This type of friction is also known as Coulomb friction. The fluid friction is developed when adjacent layers in a fluid are moving at different velocities. Let's understand the mechanism of friction. Friction exists primarily because of the roughness of the contact surface. Let's look at the contact surface of the body and the ground. No body is perfectly smooth. We can notice the roughness underneath the body, which are closely seen as peaks and troughs. Similarly, there are certain peaks and troughs on the ground surface. Now, when the body is being pulled with force P, there is a chance of these peaks of the body getting interlocked with the troughs of the contact surface. So, due to this, the body develops certain resistance for the motion, and that resistance force is called as a frictional force, which acts in the direction opposite to the main pulling force. So, frictional force F has the remarkable property of adjusting itself in magnitude equal to the applied force P till the limiting equilibrium condition occurs. So, I am just trying to show you the contact points as the resultant reactions by the ground on the body as R1, R2 and R3. Let's illustrate the mechanism of friction using a graph. Let applied force is placed on x-axis and frictional force is placed on y-axis. When the body is subjected to applied force, there will be an equal and opposite retarding force on the body, which is known as frictional force. The applied force and the frictional force are proportional to each other up to a certain limit. Once the force crosses this limiting point, then the body just starts its motion. That's called impending motion. With a very little increase of applied force, the body is subjected to be under motion. So, when the body is under static condition, that is no motion, the friction that occurred at the contact surface is said to be static friction. When the body just starts its motion, it's called limiting friction, which is maximum frictional resistance. Once the body is under motion, it's known as kinetic friction. So we have three different types of frictions. The static friction, where the body is under rest; limiting friction, which is the maximum friction when the body just starts its motion; and the kinetic friction when the body is under motion. Let's understand the types of dry friction. Static friction. It occurs when F is less than F max. That is, the body is in static equilibrium condition, which means body is purely at rest. The limiting friction occurs when F is equal to F max. That is, the body is in limiting equilibrium condition, which means impending motion, and hence F is equal to F max is equal to mu s into n is the valid equation, where mu s is coefficient of static friction. The kinetic friction occurs when F is greater than F max. That is, the body is in motion, which means F is equal to Fk is equal to mu k into n, where mu k stands for kinetic friction. The condition is impossible since the surfaces cannot support more force than the maximum frictional force. Therefore, the assumption of equilibrium is invalid and the motion occurs. The kinetic friction is less than limiting friction is less than static friction. Laws of friction. The frictional force is always tangential to the contact surface and acts in the direction opposite to that in which the body tends to move. The magnitude of frictional force is self-adjusting to the applied force till the limiting frictional force is reached, and at the limiting frictional force the body will have the impending motion. Limiting frictional force F max is directly proportional to the normal reaction. For a body in motion, kinetic frictional force Fk developed is less than that of frictional force F max, and the relation Fk is equal to mu k into n is applicable. Frictional force depends upon the roughness of the surface and the material in contact. Frictional force is independent of the area of contact between the two surfaces. Frictional force is independent of the speed of the body. Coefficient of static friction mu s is always greater than the coefficient of kinetic friction mu k, where mu k may be 25% smaller than mu s in general. And mu s and mu k are dimensionless parameters. Coming to the values of coefficient of friction, as we have already studied under the laws of friction, the coefficient of friction depends upon the material contact surfaces. The metal on metal is 0.15 to 0.60. The metal on wood is 0.2 to 0.6. The metal on stone is 0.3 to 0.7. Metal on leather is 0.3 to 0.6. Metal on wood is 0.25 to 0.5. Wood on leather 0.25 to 0.5. Stone on stone 0.4 to 0.7. Earth on earth 0.2 to 1. Rubber on concrete 0.6 to 0.9. Let's recall Newton's laws of motion. The first law: if the resultant force acting on a particle is zero, the particle will remain in the same state until and unless compelled by the external force. The first law embodies the principle of force equilibrium, which is the primary focus in the study of statics. The second law: if the resultant force acting on a particle is not zero, the particle will have an acceleration proportional to the magnitude of the resultant and in the direction of this resultant force. F is equal to ma. The second law is the basis for the most of the analysis in dynamics. Third law: the forces of action and reaction between the bodies in contact have the same magnitude and the same line of action and opposite sense. When the resultant of all the forces acting on a particle is zero, the particle is in equilibrium. Third law is the basis for understanding of force and force always occurs in pairs of equal and opposite forces. So let us understand what is angle of friction. Now, imagine a body is resting on a ground surface. This body and this is ground has a weight W, and this body is now being pulled with an external force P. For this, to understand the forces that are exerting on this body, let us draw first free body diagram. So, what is a free body diagram? An isolated view of the body considering only the external forces exerted on the body is called free body diagram. So, if this is the body, let us see what are the forces that are acting on the body. So, this body, the weight acts in this line and let the force be in this line. Then what about the contact forces that are acting at this zone? To understand this, let us have a clarity on the mechanisms of friction. Now, you look at the body and the ground. We know that no body is absolutely smooth. There are certain amount of roughness exists on the surface of every body. So, let us imagine this particular crests and peaks is the roughness underneath the body, and this crests and peaks are the roughness of the ground. Now, once both are in contact with each other, you are applying the force P. The roughness will make us consider two components of forces at the contact. One is normal, let me say N1, and the other one is frictional F1. Similarly, N2, F2, N3, F3, N4, F4, where F1, F2, F3 are frictional resistance, and frictional resistance is always a self-adjusting force. N1, N2, N3 are the normal reactions done by the ground onto the body, and they are always perpendicular to the surface. Perpendicular to the surface. So, the resultant of that I can represent as a reaction force vertically upwards and on the same line of action where the weight is acting. And the resultant of all these F1, F2, F3, F4, I can represent it as F at the contact surface in a direction opposite to the applied force. Now, the body starts impending motion once this F reaches to F max. That is what is called limiting friction. So, this is the representation of a free body diagram of the body and the ground system. Next, this let me say one representation. There is another way of representing the same system, that is with resultant force. Now, you can replace F1 and N1 with frictional resultant force R1, which is at an angle of phi. Similarly, another resultant R2 at an angle of phi 2, R3 phi 3, R4 phi 4. So what are R1, R2, R3, R4? They are the resultant forces for N1, F1, or N2, F2, N3, F3, N4, F4. So combinedly, I can represent now the same system with W as a weight and applied force in horizontal direction, and the resultant R making an angle phi with the vertical. So you can replace F max and N with R and phi. So this is another way of representing. Now let's derive what is angle of friction. Now I can resolve this R as two components, which are R cos phi and R sin phi. Right? Now, if I consider in the direction sigma fx equal to 0, then my F max is equal to R sin phi x max. Similarly, in the y direction, if I consider n is equal to R cos phi. Let me say this equation 1, this as equation 2. Now, divide this equation 1 with equation 2. That is, F max by n equal to R sin phi by R cos phi. That is, let us assume that mu, that is coefficient of friction, is equal to the ratio of maximum limiting friction divided by the normal reaction exerted by the ground on the body. So I say mu is equal to tan phi, because the ratio of sin phi by cos phi is tan phi. So phi is the angle of friction and mu is the coefficient of friction. So you remember this relation and the angle of friction. Types of friction problems. The first step in solving a friction problem is to identify its type. In the first type of problem, the condition of impending motion is known to exist. F max is equal to mu s into n. The equations of equilibrium will hold good. That is, sigma f phi is equal to 0, sigma f x equal to 0, and sigma m equal to 0. In the second type of problem, neither the condition of impending motion nor the condition of motion is known to exist. Now, to determine the actual friction conditions, we first assume static equilibrium and then solve for the friction force F necessary for equilibrium. The three outcomes are possible for this. The first one is F is, that is the frictional force, is less than maximum frictional force, that is the limiting frictional force. Here, the frictional force necessary for equilibrium can be supported and therefore the body is in static equilibrium as assumed. So we emphasize that the actual friction force F is less than the limiting value F max, and that F is determined by the equations of equilibrium. The second condition is F is equal to F max. Since the friction force F is at its maximum value F max, motion impends. The assumption of static equilibrium is valid. F is greater than F max. This condition is impossible because the surfaces cannot support more force than the maximum μsn. The assumption of equilibrium is therefore invalid and the motion occurs. The friction force F is equal to mu k into n. In the third type of problems, relative motion is known to exist between the contact surfaces and thus the kinetic coefficient of friction clearly applies. Now, let us understand the fundamentals of friction with a numerical problem, a simple problem. Consider a block of 40 newtons weight acting on a horizontal table. Then an applied force is acting on the block in horizontal direction with a magnitude of 20 newtons. Now, the weight 40 newtons causes a normal reaction in upward direction. This is the force caused by the table on the block. Now, since you are moving this block, trying to move the block with an external force 20 Newton, a frictional resistance occurs at the contact surface of the block and the table and in the direction opposite to the applied force, that is towards left. Now, the question is, if the block does not move on the table, how much frictional force the table is applying on the block? That means, in other words, calculate the coefficient of friction considering G as 10 meter per second square. Now, since the block is at rest, apply the equilibrium conditions, that is sigma fx equal to 0 in this case. That means Fs is equal to 20, this one. What is Fs? It is nothing but the frictional resistance offered by the table on the block. Now, since the block is not moving, your Fs is less than mu into n. What is n? N is a normal reaction by the table on the block. How do you obtain that? Use another equilibrium condition, Fy equal to 0, the sum of the forces in y direction is 0, that is 40 equal to n is 40 newtons. Now, coming back, if Fs is less than mu n, that means mu is greater than Fs by n, that is nothing but 20 by 40, which is 0.5. So, frictional resistance of 0.5 is acting at the contact surface of the block and the table. Now, let us understand angle of repose. Angle of repose is something that is connected to inclined surfaces. Now, imagine a body is kept on an inclined surface. It's a body, and the angle of inclination is theta. This is the ground and this is the body. Now, when theta is 0, the surface is horizontal and the body does not move. Now, as you increase the theta value, at a certain value of theta, the body just starts moving. That is, motion is impending. Now, that angle at which the body starts moving is called angle of repose. Now, let us derive the value of this angle of repose. Now, the body has a weight W, which always acts perpendicular to the ground surface. This is the ground surface, right? Now, let us represent the other forces that are acting on the body. Now, let me say first, because the body is moving downwards, obviously the frictional force is in an opposite direction to the motion, that is in upward direction, F max, right? Then there is a normal reaction acting on the body by the inclined surface, that is this surface, right, which is again perpendicular to the inclined surface. Now, here there are two surfaces shown in the figure. One is the ground surface, the other one is the inclined surface. Now, let me call ground surface as x dash and inclined surface as x double dash and x triple dash. Okay. Now, if I take the y axis of this becomes y dash and this becomes y double dash and y triple dash. Okay. So, there are two axes here. Let us resolve all the forces on one axis. For example, I shall consider the x double dash x triple dash as the axis for all the forces to represent. See, this is the inclination x double dash when x triple dash, and I draw a normal which is y double dash and y triple dash. Now, on this, the W is the weight of the object is acting at an angle of theta, say theta, with respect to y double dash and y triple dash. So, represent that angle of W here at an angle of theta, whereas N is already lying on the y axis. So, I represent N here along y double dash, y triple dash. Then you have force, frictional force F max lying on the x axis directly. So, the only force among the three forces, that is W, is inclined to an angle of theta to the vertical y double dash and y triple dash. So, let us resolve this force onto this y axis and x axis. Since this is theta, we get this as W cos theta and this as W sin theta. Right. Then I consider the conditions of equilibrium here as sigma F x double dash x triple dash equal to 0. Then I get as F max equal to W sin theta. Let me call this as equation 1. Then you have sigma F y double dash y triple dash equal to 0. Here this downward force is equal to upward force, that is N equal to W cos theta. Right? Now, let us divide equation 1 by equation 2. We get F max divided by N equal to tan theta. We already know that mu, which is equal to F max by N by assumption, is equal to tan phi. So, I represent tan phi in the place of F max by N and say tan phi equal to tan theta or phi equal to theta, where phi is said to be angle of repose. So, when the friction angle of repose is equal to the angle of inclination, the body starts its impending motion. So, this is what is called angle of repose. There is another way of representing the free body diagram with respect to R. That is, you can draw the inclined surface, okay, and the line of action of force where W is acting. W always act perpendicular to the ground surface, remember. Okay, then the resultant of this acts as a collinear force on the same line of action at an angle of phi. At an angle of phi. Okay. So, this is another way of representing the resultant force, replacing F max and N for the problem. 4 different situations may occur when a rigid body is in contact with the horizontal surface. Let us understand case by case. In the first case, the P applied force is acting in the vertical direction. So, there is no friction between the contact surfaces. Hence, Px, that is the resolved component of P in x direction, is 0 and frictional force is also 0. Coming to the second case, in this case, the P is pushing the body towards the right direction. The P applied at a smaller angle with the horizontal line. Now, when the P is resolved, the resolved components Px and Py will contribute to the different actions. The Px contributes in moving the body towards right direction, and Py does not contribute for the motion of the body. Now, this Px is having an opposite reaction force from frictional effect, that is F. So, if the Px is less than Fm, then there is no motion causing in the body. So, there is no evidence that the maximum frictional force has been reached. F is not equal to Fm, which is equal to mu s into n. Now, in the third case, if you just increase the angle or change the angle, for that matter, change the angle of application of force with respect to the horizontal line, then the motion may impend when Px is equal to Fm. If the body just about to slide, then F is equal to Fm is equal to mu s n may be used. In the fourth motion, that is, if the angle of application of force with respect to the horizontal line is again changed, slightly increased, then there can be a motion when Px is greater than Fm, or otherwise Fm is equal to mu k into n. Now, let us understand the same phenomenon with respect to the resultant force R. That means, we are replacing the F max and N with R. In the first case, there is no friction, and you notice that the resultant force R is equal to N. In the second case, there is a resultant force R which is at an angle of phi with respect to the normal reaction. And there is no motion, therefore tan phi s is equal to Fm by n, which is equal to mu s n by n, that is equal to mu s. In the third case, where the motion just starts impending. Then the fourth case, there is a kinetic friction occurring at the surface. So tan phi k is equal to Fk by n, which is equal to mu k n by n is equal to mu k. Then in the next situation, where we consider the inclined planes. In the first case, if you see the horizontal surface where theta is equal to 0, so there is no friction and theta equal to 0. In the second case, where the horizontal surface is inclined to an angle of theta, and if this theta is less than phi s, then your resolved components n is equal to w cos theta and f is equal to w sin theta. And if this phi is less than phi s, there is no motion in the body. Coming to the third case, where theta is equal to phi s. That means you increase the theta such a angle that the body just starts sliding. That is called motion is impending. In that situation, your R and W are collinear. They're both the line of action of forces lie on the same line. Then comes the fourth case, where the theta is greater than phi s. The resolved components n is equal to w cos theta and f max is equal to fm. So if n tan theta is greater than n tan phi, w sin theta is greater than f max, then f is equal to mu k n, phi is equal to phi k, that is equal to less than phi s, which is less than theta. R is not vertical. Forces acting on block are unbalanced motion. Now let's start solving some problems. The question here is, there is an object placed on an inclined surface which is having an inclination of 30 degrees from the ground surface. The weight of the object is 200 newtons and the ground surface has a friction of 0.3. Now a 300 Newton force externally applied on the object so as to resist the sliding motion of the body. Now the question is 300 Newton sufficient to stop the sliding of the body on the inclined surface at an inclination of 30 degrees. So let us check through the problem if this 300 Newton is adequate enough to hold the body on the inclined surface. For any problem in engineering mechanics, there are 5 major steps to be followed. Step 1 is understand the problem. 2. Sketch free body diagram. 3. Resolve the forces. 4. Apply equilibrium conditions. And 5. Solve the simultaneous algebraic equations and understand the result. So in short, I can say understand, sketch, resolve, apply, solve. This is applicable to all problems of engineering mechanics. Now, the second step, that is sketch the free body diagram. I can draw the free body diagram for this on inclined surface. Let me say xx dash. and y dash. See, the W is the force placed here. Obviously, this makes an angle of 30 degrees with the y dash plane. Then you have a 300 Newton acting at same 30 degrees to the plane surface parallel to the inclined surface. So, you have a 300 Newton force acting at an angle of 30 degrees with this. Now, if you imagine the body is sliding down, your frictional force acts opposite to the sliding motion, that is in upward motion, that is F. That is F. Then you have a normal reaction that is perpendicular to the inclined surface, which occurs at this position. The weight of the compound body is 200 newtons. Agreed. Now, you have 4 forces here. One is the weight, the other one is the reaction, then you have applied force, and then frictional force. Let us first resolve the forces onto the x and y axis. So, this is 30 degrees with this. Obviously, this becomes W cos 30 and this component is W sin 30. Now, when this is 300 inclined at 30 degrees to the x axis, so this becomes 300 cos 30 and this becomes 300 sin 30. So, now we have resolved both the forces and all the forces are now on along x axis and y axis. Let us now assume the forces that are shown in this direction are positive and the forces that are shown in this direction are negative. Similarly, forces that are shown in upward direction in y axis are positive, forces that are shown downward direction on y axis are negative. Sign convention. Then we have finished first understanding sketch, then was resolve forces we have completed. Next one is apply equilibrium conditions. Applying equilibrium condition, first one is sigma fx equal to 0. In sigma fx equal to 0, what are the forces that are acting on x axis? F, W sin theta, 300 cos theta. So, F in that direction is positive, F positive, W minus W sin 30 because this is negative direction, this is again positive direction plus 300 cos 30 equal to 0. Let me call it as equation 1. Since I know W as 200 Newton, substitute that value, get F as around 160 newtons. So, for the balance to exist, the frictional resistance here is 160 Newton required. Now, you should know what is the actual resistance existing at the contact surface, which is more or less the depending on mu of the contact surface. Now, to get that, what you do here is you take the next equilibrium condition sigma Fy equal to 0. In sigma Fy equal to 0, look at the forces acting on y axis. One is W cos 30, 300 sin 30 and N. Now, follow the sign convention. Forces acting in upward direction, that is N positive, and downward direction W cos 30 and 300 sin 30 negative. minus W cos 30 minus 300 sin 30 equal to 0. Now again substitute W as 200, you get solved for N, it is coming around 323 newtons. 323 newtons. Now let us calculate the limiting friction F max is equal to mu into N. Given mu as 0.3, N as 323, coming around 97 newtons. Around 97 newtons. So here the maximum limiting friction is 97 newtons, whereas the required one is 160 newtons. So F is greater than F max. That means the body will not slide and the 300 Newton is adequate enough to balance the body on the inclined surface without sliding down. So before we go to the next problem, let me explain some fundamentals about moment of force. So the moment of force is the turning effect of a force, and it is mathematically represented as force multiplied by the distance from axis. So the mathematical expression for moment is F into D. F into D. Now here I am teaching you in a scalar method and not in vector method. We can deal vector method at later stage. Now let me explain you with some cases. Now this is one particular case where a rod of length L is fixed at one end and a force F is acting on the free end. The rod length is of L. Now in this case, how do you calculate the moment caused by the force F? The free body diagram for this could be, since it is fixed on both sides, it can be written as RAX and RAY as reactions, and F is the force acting at a length of L. So let us calculate the moment occurred at A due to F. The force vector, the direction of the arrow is in downward direction. So you can consider clockwise effect as positive and counterclockwise effect as negative in all our calculations. So to calculate the moment about A by the force F, you hold the force F here and rotate the force towards A. That means it has to move this way. That means the moment about A is, as I said, product of force and distance. The force is F multiplied by the distance is L. The next immediate thing is the sign convention. As I said, if the moment is clockwise, consider it as positive. So this is a clockwise movement. Therefore, this becomes positive. Now, let us consider this particular case. In this case, the force is acting upward direction, and again you have the constraint here which creates the reactions RAX and RAY with L span length. Now this time you have to take the moment about A by rotating the force towards the constraint, that means this direction, this direction. Therefore, MA is again F into L, however, it is in anti-clockwise direction, so the sign convention becomes minus. Now, let us take another case where you have more forces and more constraints. Now, this is a rod, AB is a rod fixed at one point A and hinged at another point B. Now, there are two forces acting on the rod, F1 which is inclined at an angle of 30 degrees and is a distance of L1 span length from A. Another force F2 acting vertically downward direction at point D. The total span length is L and the points of force are located at L1, L2 and L3. Now, let us calculate the resultant moment for this system. For this, you draw the free body diagram as again the reactions acting here are RAX, RAY, okay, and this is a hinge. A hinge again has RBY and RBX. Now, this force has to be resolved to x component and y component. So, let me mark point C, point D, and point C F1 is now resolved to F1 cos 30 and F1 sin 30. The next force is F2 here. Now, let me explain you the moments both at A and B. Now, suppose if I take moment about A, that means sigma MA equal to 0. I am taking moment about A. Now, what are the forces that contribute to the moment about A here? F1 cos theta 30 degrees does not cause any moment about A because it is lying on the same line. That means there is no perpendicular distance to cause the moment. So, this does not cause any moment. Then F1 sin 30, yes, it contributes to this moment here. F2 contributes to the moment. RBX does not contribute because again it is lying on the same line of axis, but RBY contributes to the moment here. So, you have three forces that contribute to the moment about A. Now, step by step let us see. F1 sin 30, if I rotate F1 sin 30 force vector towards A this way, so I get F1 sin 30 multiplied by L1. Since it is clockwise, I put positive. The next one is F2 rotated towards the constraint A is again clockwise. So, plus F2 into L1 plus L2, L1 plus L2. Then you have RBY rotated towards A, which is anti-clockwise. So, minus RBY multiplied by total length L, that equal to 0. So, if you know F1, F2, L1, L2, L3, you can calculate RBY from this relation. That is the reaction at B, that is a hinge reaction in vertical direction. Now, let us take moment about B this time. Let us take moment about B. That means sigma mb equal to 0. So, when you are taking moment about B, let us understand what are the forces that again cause for the contribution. RAY can give moment, but RAX does not give moment. F1 sin 30 can give moment, F2 can give moment, but RBY cannot give again, and RBY and RBY both cannot give, because you are taking that as a moment center. Now, taking moment about B now, let us start with RAY. Now, RAY, which is vertically upwards, has to rotate about B, So, when I am rotating about B, the moment here is, let me mark in a different color, moment here is clockwise, right. So, clockwise RAY multiplied by L plus. Now, this time F sin 30 is rotating in the other direction, this direction. That means minus F1 sin 30 into L minus L1 or L2 plus L3. Then F2 rotated in towards the moment center B is again counterclockwise. So, F2 multiplied by L3 is equal to 0. So, having known the values of F1, L, L1, L2, L3, you can calculate RAY from this relation. So, if you have the clarity about the moment centers and the distances that has to be considered to calculate the moment of force, then we can solve some more problems in this direction. Let us start problem number 2. Now, in this problem, there is a bar of length 10 meters placed on the two rough inclined surfaces. The weights 100 Newton and 200 Newton are acting on the bar, and the bar is negligible weight. It has a negligible weight. Now, let us draw a free body diagram for this system. Now, this is 100 Newtons and this is 200 Newtons. So, the higher weight is on this side. Now, because the weight is more here, the bar tends to move downwards, and here it tries to move upwards. Okay? So, based on this motion, we can represent the frictional force direction. Now, let us first draw the free body diagram for the figure. The free body diagram goes as the bar, okay, the rough surface this way and this way, the forces 100 and around 200 at a distance of x from one surface, at a distance of 2 meters from here, and the total span length is 10 meters, right. Now, the inclined surface will exert a reaction on the bar, which is, as I always said, perpendicular to the surface. I call it as NA. Now, the angle of this is 30 degrees. So, when this is 30, this becomes 60. Okay? This becomes 60. Then, as I explained, because the body here moves down and here moves up, the resistance, frictional resistance will tend to move downwards. Therefore, the frictional resistance, that is FA, if I call, is in downward direction. Right? Now, let me draw one horizontal and vertical line so as to know its position on the x and y axis. Let me call this as x axis and this as y axis in our problem. So, if this is 60, then this could be 30. This could be 30. Similarly, look at this. The reaction here, the same exercise, but NB, and this angle is 60, therefore this angle is 30. Since the body is moving here downwards, your frictional resistance is upwards. Okay? So, I can draw another axis for this as 60 with the horizontal. Now, let us resolve the forces that we are representing here. If NA cos this thing, then you have this as NA cos 60 and this as NA sin 60. FA is in downward direction. So, this is FA cos 30 and this is FA sin 30. Now, if it is NB, then your resolved component NB cos 30 and NB sin 30. FA in that direction gives you FA cos 60 and FA sin 60. So, now let us apply equilibrium conditions, that is sigma Fx equal to 0. So, what are the forces that are acting in x direction? This one, and this one. So, mark x in this direction is positive, in this direction is negative. Then you have FA cos 30 positive plus NA sin 60, because it is also towards right, plus FA cos 60 minus NB sin 30 equal to 0. Call me as 1. Here FA is equal to mu into NA. Mu happen to be same here and here. Okay, if there are two different surfaces, like one is metal surface, the other one is earth ground, then mu values would be different. Now, next equilibrium is Fy equal to 0. So, let us see the forces acting in y direction. Let me say this and this. Now, y in upward direction is positive and downward direction negative. So, look at let us start from here. It is in downward direction. So, minus FA sin 30 upward direction plus NA cos 60, this one minus 100 minus 200 plus FA sin 60 plus NB cos 30 equal to 0. Equation number 2. Now, your FB is equal to mu into NB. If you have, oh, I'm sorry, this should be represented as B and this is also B, right? So, this becomes FB. B. So, FB is mu NB, FA is mu NA. Okay. Now, These two are not sufficient for us to get the value of x. The question is, how much is x? Not possible to calculate x from the two equations. So, you need to go to the third equilibrium condition, that is sigma m equal to 0. So, the moment occurs both at A as well as at B, that is sliding, right. So, the moment occurs at both the places. So, it is your choice to select which point has to be considered for the equilibrium equation. So, let me consider A for moment, ma equal to 0. So, if I have to take moment about A, that is this point, let me see what are the forces that are actually contributing to the movement about A. So, if these forces cannot contribute as they are on the same axis, these forces cannot contribute. They cannot contribute because they are all lying at this same axis of moment center. But you look at 100, yes, this contributes, 200 contributes, FB sin 60 contributes, FB cos 60 contributes, NB sin 30 contributes, NB cos 30 contributes. So, 1, 2, 3, 4, 5, 6, all 6 forces can contribute to the movement about A. So, step by step, let us put down those values of movement. As we said, movement is force into distance from the axis. Now, this is the force, this is the movement center. So, rotate the force which is in vertically downward direction towards the movement center this way, this way. So, here in movement again, let me recall, clockwise is positive, counterclockwise is negative. So, here this is clockwise, I call it positive, where force here is 100 multiplied by the distance here is 2, 100 into 2. So, the next force that contributes to the movement is 200, which is vertically downward direction. So, 200 taking movement about A in this direction, rotate it in this direction, which is a clockwise direction. And the distance from the movement center is 10 minus x, 10 minus x. So, the moment value is force 200 into 10 minus x. Then comes your FB sin 60. FB sin 60 having in vertically upward direction, looking at the movement center in this direction. So, that goes in counterclockwise direction, minus FB sin 60 multiplied by the distance, that is nothing but the span length, into 10. Then your FB cos 60 cannot contribute to the movement because it is lying on the same axis. Similarly, your NB sin 30 cannot contribute because it is lying on the same axis. Then your NB cos 30 here will contribute to the movement in moving in counterclockwise direction, that is minus NB cos 30 multiplied by 10, multiplied by 10, that is equal to 0. So, this is the equation number 3. So, if you solve the unknowns FB and NB from these equations and substitute them here to get x. So, all the 3 algebraic equations are solved and the unknown is calculated. Now, the x here becomes around 3.01 meters after calculation. So, this distance from here is around 3 meters from the rough inclined surface. Let us start the next problem, problem number 3. There are 3 blocks A, B, C of different weights and different materials placed on an inclined surface which is having an inclination of 20 degrees with the horizontal surface. Now, the mass of block A is 60 kg, the mass of block B is 40 kg, the mass of block C is 20 kg. Let us assume the gravitational acceleration due to gravity as 10 meter per second square. Now, the coefficient of friction in static and kinetic conditions for A and C are 0.5 and 0.4, and coefficient of friction for static and kinetic are 0.3 and 0.2 for B. That means that A and C are, say, one material and B is a different material, because the surface is common to both. That is the reason you have different coefficient of frictions. Now, the question is, does the three blocks slide down at this particular angle of inclination? That there is no external force acting on it, only based on the gravity or self weight of the bodies. We should check if the bodies will slide down the inclined surface. Let us start with body C. The body C, will draw the free body diagram for body C. The free body diagram of body C goes this way. Normal. The weight always is perpendicular to the ground surface. Okay, don't draw the ground surface here. This is WC, which is MC into G. Okay, if this is 20 degrees, so this is 20 degrees and this is NC. You resolve this to weight component MCG cos 20 and MCG sin 20. Now, let us assume that it is sliding down, then the frictional resistance will be in upward direction, calling it as Fc. Okay. Now, apply the equilibrium condition in y direction, Fy equal to 0. So, the sum of the forces acting upward and downward equal to 0. So, Nc minus Mcg cos 20 equal to 0 is the one expression where you can calculate Nc. Now, check if the block C is sliding or not. That is the first question. To check that, you have to calculate the frictional resistance offered by the body on the inclined surface. That is, calculate this value. That value is, you can say, sigma fx equal to 0, where Fc is equal to Mcg sin 20. Substitute the value of Cg20, that is 20 into 10 into sin 20. After this, you have to find the frictional force that resists the motion in downward direction. That is mgc sin 20. So, if you calculate mcg sin 20, substituting these values mc20, g10 sin 20, you are getting around 68.4 newtons. Now, you have to calculate the available frictional resistance at the contact surface. The available frictional resistance at the contact surface here is obtained from the expression mu c into ns. Mu s into ns from equation 1 can be considered as 20. Mu s for block C 0.5 into MC 20 into 10 into cos 20, giving you around some 93.7 newtons or so. So, since this available frictional resistance is higher than the frictional resistance offered, so Fc is greater than the downward motion, the body will not slide. Body C will not slide. So, the next body, let us calculate for A. For body A, you need to do the same exercise. Body A, this is MAG, NA 20 degrees here. So, calculate MAG with this as 20 degrees, MAG cos 20, MAG sin 20, okay, and this is FA. So, first sigma Fy equal to 0, the same exercise, Na is equal to MAG cos 20, then find out the downward force. The downward force here is MAG sin 20, you write MA 60 into 10 into sin 20 is coming up around 205 newtons. Then find out the frictional resistance which is given as mu s into Na, and that is mu s into MAG cos 20, and this comes around 232 newtons. So, here again your Fc is greater than your downward force. That means, your Fa is greater than downward force. That means body A will not slide. Now, the next aspect is about C. Now, the similar exercise has to be done for body B. This is body B, MB, G, NB, and you resolve this MBG sin 20, MBG cos 20, right. Now, if you calculate in this particular force, the downward force happens to be 136 newtons for this value, and frictional force happens to be around 112 newtons. That means, which is something different from the above two. That is, Fb is less than your downward force. So, that means the frictional resistance offered here is less compared to the downward force component. So, in that case, B has to slide down because it does not have sufficient limiting friction. However, in this case, there is a great resistance by A on body B. Since there is a great resistance by A on body B, the body B does not slide. If there is no body A here, definitely the body B will slide because it cannot afford more frictional resistance. So, in a nutshell, you can say that all three bodies are held on the inclined plane without sliding. Now, let us move to the problem number 4. It is quite interesting problem. A cylinder of weight W is placed on a V block and the cylinder surface touches the V block on both sides. Now, how much force P is required to pull the straight cylinder from the V block? So, this is the front view, this is a V block and this is a straight cylinder. W is the weight of the block and you are trying to pull the block from the V block. Now, you look at the side view, this is a V block of having an included angle 2 alpha and W is representing the weight of the straight cylinder resting on V block. Now, to solve this problem, it is important to visualize the problem as a whole. Now, let me draw the complete picture of this V block. Right, and the cylinder is resting on this V block whose weight is W. So, these are the contact points. This is alpha and this is alpha because the included angle is 2 alpha. Then the force is applied in this direction to move the cylinder outwards. Now, when you notice the contact points, since the external force is acting outwards this direction, the frictional force at the contact surfaces will act in opposite direction. Let me call F. Then the cylinder having in touch with the edges of the V block will create reaction forces N. So, because N is the normal reaction exerted by the V block onto the cylinder on both sides. So, let me call this as alpha, similarly this also alpha. That means, if I resolve this normal reaction, this becomes N cos alpha and this becomes N sin alpha and this becomes again N cos alpha and N sin alpha. So, let me draw the free body diagram from this point of view, So, if you have the cylinder and this is the weight, then the normal reaction is 2n sin alpha because you have two vertical resolved components of the reactions 2n sin alpha. Then you have two frictional forces along the length of the cylinder. When P is acting this way, the frictional resistance, that is 2F, acts in this way. Now, let us calculate the value of P, which is of our interest. Sigma Fx equal to 0, P is equal to 2 into F, that is 2 into mu into N. Now, sigma Fy equal to 0 gives us W equal to 2n sin alpha, or n equal to W by 2 sin alpha. Now, substitute, let us call this as equation 1, equation 2, substitute to n in equation 1, that gives us P is equal to 2 into mu into W by 2 sin alpha, where P is given as mu W by sin alpha. So, the amount of force that is required to move the cylinder from V block depends upon the coefficient of friction, the weight of the straight cylinder, and the V angle, half of the V angle. So, these are the parameters that influence the motion of straight cylinder from the V block. Let us understand D'Alembert's principle for a dynamic condition. The system of forces acting on a body in motion is in dynamic equilibrium with the inertia force of the body. Let R be the resultant of all forces, then according to the Newton's second law of motion, R is equal to ma, where m is the mass of the body, a is the acceleration. According to D'Alembert's principle, R minus ma equal to 0, where ma is the force of magnitude applied in opposite direction of motion and is termed as inertia force or reverse effective force. In general, when a body is in under translation for a rectilinear motion, the D'Alembert's equations are sigma Fx equal to ma x and sigma Fy equal to ma y, or otherwise you can express as sigma Fx minus ma x equal to 0 or sigma Fy minus ma y equal to 0, and these are said to be dynamic equilibrium conditions. For a curvilinear motions, sigma Fn minus man, that is normal acceleration, equal to 0, where normal acceleration is given as v square by r, and sigma Ft minus mat equal to 0, which is at tangential acceleration, is given by dv by dt. So, it is preferred to use D'Alembert's principle, since just by applying a reverse effective force, the moving body can be treated as a body in equilibrium and analyzed by using equations of static equilibrium. Now, let us solve some problems in friction which are subjected to motion and under dynamic condition. The problems connected to dynamic condition are based on D'Alembert's principle. So, D'Alembert's principle basically talks about the dynamic equilibrium condition, in which the equilibrium condition is stated as sigma Fx minus max equal to 0. This is the net forces in x direction, where sigma Fx is the external force sum and max is the inertia force, and sigma Fy minus may equal to 0 and sigma m minus I alpha equal to 0. Now, coming to the problem, we have two weights 200 Newton and 800 Newton connected with a thread. These two blocks or weights pulled by an external force 400 Newton in the right direction. Now, the surface friction, which is mu is equal to 0.3 for both the blocks. Now, the question is, calculate the tension in the thread and the acceleration of the system. Now, let us solve step by step. First, consider the free body diagram of 200 newtons. Now, since the body is already in the motion and the motion is in the direction of external force, that is in rightward direction, the inertia force and the frictional force acts in opposite direction. So, considering the free body diagram, that is, you have this 200 Newton, here and a normal reaction on the same line of action. Then you have tension, because this is a tension, you have the tension here in the thread, and there is a frictional resistance. Let me call this N1, so F1. Now, since the body is moving in the right direction, there is an inertia force which is given as W by G, or I can say W1 by G into AX. I am showing A suffix x is acceleration in x direction. If you assume that this is x direction and this is y direction, in this system the body is moving only in x direction. There is no motion in y direction. So, that is the reason we have to specifically mention A suffix x, that is mass into acceleration, which is the inertia force. Now, these are the forces that are acting on the body. Now, in this forces, apply this dynamic equilibrium condition, that is sigma Fx minus Max equal to 0. That is the sum of the forces in x direction. Those include this as well as this. That is, you can say plus T minus F1 minus W1 by G into Ax equal to 0. Here F1 is equal to mu into N1. Now, how do you get N1? Since there is no motion in y direction, you just have to simply apply the equilibrium condition sigma Fy equal to 0 and N1 is equal to 200 newtons. So, these are the set of equations for the free body diagram of 200 newtons. Now, let us write down the equations for 800 newton. The 800 newton body has the forces. One is the weight, the other one is the reaction N2. This is the tension T, because this T and this T creates tension in the thread, and there is an external force 400. Since the motion is in this direction, there is a frictional resistance F2 here and inertia force, let me say W2 by G into Ax. Now, write down the equilibrium conditions. Sigma Fx minus Max equal to 0 here. The net forces here are 400 positive minus F2 minus T minus W2 by G into Ax equal to 0. So, let me call it as equation 2, where F2 is equal to mu into N2. And again here, since there is no motion in y direction, you have to just apply sigma Fy equal to 0, where N2 is equal to 800 newtons. So, you apply equation from equation 1 and 2, you can calculate the tension and the acceleration. So, 2 unknowns and 2 simultaneous equations. So, tension is around, if you calculate, comes around 80 newtons, acceleration is 0.981 meter per second square. So, this is how you apply D'Alembert's principle to the system. Now, let us go to the next problem, problem number 6 in dynamic conditions. Now, there is a system of bodies. One is 1200 newtons connected to another 800 newton body with a rope. So, the body is now moving up on the inclined surface which is at an angle of inclination 12 degrees. The question is, what is the tension in the string, the acceleration with which the body is moving up. The second thing is, when this body started from rest, after the motion 3 seconds later, what is the distance covered by this body is the question. The coefficient of friction on these two is given as 0.2. Now, again we need to apply D'Alembert's principle step by step. So, let us first take this, the inclined surface body. Now, in the inclined surface body, this is 12 degree, right. Now, this is the weight, that is 1200 Newton, which is again perpendicular to the ground surface, and then you have normal reaction N perpendicular to the inclined surface. There is a tension in the string by this, okay. Then the body is in motion in upward direction. So, there is a frictional resistance F and inertia force, that is 1200 by G into AX. I consider this as X there, because Y there is no motion, there is only motion in X direction. Now, let us resolve all the forces in this plane, So, this is 1200, 12 degrees. So, this becomes 1200 cos 12, this becomes 1200 sin 12, this is F, and further this is T, this is N. Okay. So, we have considered all the forces, right, force F and T in the other direction. Then you have one more inertia force, that is 1200 by G into AX. So, writing down the D'Alembert's principle, sigma Fx minus MAX equal to 0. See, what is the net force? This minus 1200 by G into AX minus 1200 sin 12 degrees minus F plus T equal to 0. This is equation number 1. Then, what is F? F is equal to mu into N. Now, you need to determine what is N. For that, since there is no motion in Y direction, you just have to take sigma Fy equal to 0, where N is equal to 1200 cos 12 degrees. Substitute this value of N into the equation and get the, you have still two unknowns, one is A, other one is T. So, you need one more equation to solve the equation. The next thing is, go to the body number 2, 800 newtons. So, this 800 Newton has a weight acting downwards and there is a tension in the string. Since the weight is not in contact with any surface, frictional resistance does not act on the body. However, the body moves in downwards. So, the motion is in downward direction. Since the motion is in downward direction, your inertia force, that is 800 by G into AY, is in upward direction. Now, this Y direction there is a motion, there is no motion in X direction. So, these are the forces that are acting on the body. Now, the D'Alembert's principle, sigma Fy minus MAY equal to 0, that is T minus 800 minus 800 by G into AY equal to 0. Since the acceleration is same, you can consider Ax equal to Ay, and considering this as equation number 2, solve these two simultaneous equations 1 and 2 and derive the tension and acceleration. So, if you solve these two unknowns and two equations, you get tension around 673 newtons and acceleration around 1.98 meter per second square. So, okay, the first two unknowns are calculated. The next question is, what is the distance covered by this 800 Newton which is started from the rest after 3 seconds? So, apply the equation of motion to the body as S is equal to ut plus half at square, given u as 0 and t as 3 seconds, and acceleration which is obtained as 1.981 meter per second square. You substitute that and solve the value of the distance travelled. This, it is coming around 6.7 meters or so. The distance travelled by 800 Newton is 6.7 meters. Now, let us solve problem number 7. The problem number 7 is, the bicycle is rolling on an inclined surface which has an inclination of theta. Theta is the slope of the surface. Now, 2a is the distance between the centers of the front wheel and the rear wheel. The weight of the bicycle lies at a point G, which is at a height of h from the inclined surface. X is from the middle point, which calculates to be a minus x and a plus x. Now, the question is, what is the greatest slope theta for the bicycle to rest without slipping? If one condition is the rear wheel is braked, the second condition the front wheel is braked. So, let us start first with when the rear wheel is braked. Okay. So, let me draw the free body diagram. You have the front wheel here with its center, the rear wheel with its center here, right. Then we have the weight acting at a height of g, right. So, the weight always acts perpendicular to the ground surface, right. Now, this is the front wheel, this is the rear wheel. The reaction, normal reaction, is always perpendicular to the surface, inclined surface. I call it as NF, and the normal reaction on the rear wheel, call it as NR, right. Now, the wheels are rolling in this direction. The first condition is the rear wheel is braked. Now, when the bicycle is rolling down, the motion in this direction, the wheels rotate in anti-clockwise direction. Therefore, while rolling, the friction actually lies downwards. But here, the condition is rear wheel is braked. That means a brake is applied at the rear wheel. Then the friction will act in opposite direction to the motion, right. Now, this is what is called frictional force when the rear wheel is braked. That means when a brake is applied to the rear wheel, the frictional force acts in the upward direction. Now once you know this, let us resolve all the forces on this x dash, y dash, y dash. On x dash and y dash, this thing. Now if I resolve this way, then what happens? This is theta, right? Then I can resolve this as w cos theta and w sin theta. Now let us put all the forces in xx dash and yy dash direction. X dash, y dash direction. Then you have on the top w cos theta, right? Now towards left is w sin theta, then towards right is frictional force, then you have, I can say n r and n f upwards. So these are the forces that are acting on the system, okay, both inclined surface and the wheels. Now you write the equilibrium conditions for this. First is sigma fy dash equal to 0. We have w cos theta equal to nr plus nf, that is equation number 1. Then sigma fx dash equal to 0, we have w sin theta equal to fr, which is equal to mu into nr. Let me call it as equation number 2. Now for us the unknowns here are theta is one unknown, and what do you have, w is also an unknown, weight of the vehicle is not given to you, and we have even nr, nf are also unknowns. So more number of unknowns are more than the equations. So let us write one more equilibrium equation. Let me call this point as B and this point as A. So I will take moment of the forces about B, right? So let me call sigma mb equal to 0. Sigma mb equal to 0. Let us look at the forces that contribute to the moments. One is w sin theta, the other one is w cos theta, the one more is nf. Now we know these distances, this as a plus x, this as a minus x, and the whole of it as 2a, right? Now let me take first nf. The moment caused by nf about the point B. See, nf is in the upward direction. It is rotating about B in this direction, which is clockwise. We already have the convention, clockwise is positive, counterclockwise is negative if you take. So this clockwise, force is nf, distance is 2a. So let me say plus nf into 2a is one moment. Then w cos theta, which is in downward direction, if it takes moment about B in this direction, it goes in this direction. So with a distance, perpendicular distance a plus x, that means w into cos theta into a plus x. Then one more force, that is w sin theta. W sin theta, the perpendicular distance about this point is h, and this has to take moment about this point in this direction. That means it rotates in this direction, anti-clockwise direction about B. Okay, so about B, I can say minus w sine theta into h equal to 0. Equation number 3. So you have 3 simultaneous equations wherein you can calculate the unknowns nr, nf and w, and then finally get your tan theta value. So the slope can be obtained from here as tan theta equal to mu into a minus x by 2a plus h nu. So this is the value of the slope required for the bicycle to rest on the inclined surface when the rear wheel is braked. Means a brake is applied on the rear wheel. So the next question is, when the front wheel is braked. When the front wheel is braked, the same procedure, but apply the frictional force on the front wheel. That goes this way. I shall draw the free body diagram. Okay, this is the front wheel, this is the rear wheel. Okay, let me call this as W. Again, this is theta, so this becomes W cos theta. This becomes W sin theta, this is NF, this is NR, NR. The only difference is this time the vehicle, we are considering the front wheel motion, and the friction on the front wheel once the brake is applied is in the upward direction, FF. Now do the same exercise of resolving the forces and write down the equations of equilibrium sigma Fy dash equal to 0, which comes to be again W cos theta equal to NR plus NF, that's equation 1. Fx dash equal to 0 is again W sin theta equal to FF, that is mu into NF, equation number 2. Now this time the moment we take it at front wheel contact point, that is sigma MA equal to 0. Now in sigma MA equal to 0, you have the equation about moment about this happens to be, this is H, we know that, and this is 2A, and this is A minus x, and this is A plus x. Okay, now we have NR again in counterclockwise direction, minus NR into 2A, then W cos theta goes this way, that is clockwise direction, plus W cos theta into A minus x, W sin theta into H again minus W sin theta into H, okay, equal to 0 is equation number 3. Now you get tan theta as mu into A plus x divided by 2A minus h nu. This is the slope that is required for the vehicle to rest on the inclined surface when the front wheel is braked. So this is how you calculate the frictional forces and the required greatest slope. Now let's look at problem number 8. A 750 Newton crate rests on a 500 Newton cart. So this is a 750 Newton crate resting on 500 Newton cart. The coefficient of friction between the crate and the cart is 0.3. So at this contact surface the friction is 0.3. And the coefficient of friction between the cart and the road, that means near the wheel contact surface, the coefficient of friction is 0.2. If the cart is to be pulled by a force P such that the crate does not slip. Then determine the maximum allowable magnitude of P and the corresponding acceleration of the cart. So, here we need to solve this particular problem by using two free body diagrams. One is for the 750 Newton crate with the frictional force and weight, and the next free body diagram is on 500 Newton cart with external force P and frictional force acting at the contact surface of the wheel and the road surface. So this solution is available in the notes provided in the description link. Now let's look at problem number 9. Two blocks A and B are released from rest on a 30-degree inclined plane when they are 18 meters apart. So this is A, this is B, placed on an inclined plane at an angle of 30 degrees. And these two blocks are at a distance of 18 meters, and now they are released from rest. The coefficient of friction under the upper block A is 0.2 and under the lower block B is 0.4. That means it is indicating that the materials of block A and block B are different. In what time block A reaches the block B? What will be the contact force between them? The weights of block A and B are A is 100 Newton and B is 80 Newton respectively. So this problem solution is also available in the notes provided in the description link. Session 2. Applications to friction. Let us study about wedges, connected bodies, ladder, belt friction and rolling wheels. Wedges. A wedge is one of the simplest and most useful machines. A wedge is used to produce small adjustments in the position of a body or to apply large forces. Wedges largely depend on friction to function. In the figure, block A supports a load W and is to be raised by forcing the wedge B under this. The contact reactions between the blocks at this common surface are not only equal and oppositely directed on the free body diagram of each block, they also act so that their tangential or frictional components along the normal contact surface oppose the impending motion of each block relative to the other. So this is the wedge and this is moved with an external force P so as to raise the block on which some weight W is placed. So for the wedge to slide out of its space, slippage must occur at both the surfaces simultaneously, otherwise the wedge is self-locking. So wedge is in contact with the ground as well as with the block A. Okay, now let us understand the concept of wedge with more clarity. Okay, so as I said, wedges are machine components that are used to raise the or lift the heavy objects. Now look at this figure. This trapezoidal geometry is a wedge and this is a block placed on the wedge, and suppose there is some W, another weight. It can be a machine or it can be something very heavy heavy objects placed on the block which has some tons of weight is kept on the block. Now the objective is to move this weight in upward direction, that means to raise the weight. For this to move up, that means the block has to move up. For this to happen,
we apply a force P on the wedge such that the wedge moves in rightward direction. Because of this inclination, the block starts raising on the wedge. Thereby, the machine or the heavy object that is placed on the block also raises along with the block. Now, let us understand the forces that are involved in this entire mechanism. Okay. Now, I shall solve this problem in two methods. Method 1 is resolution of forces. Method 2 is vector method. Okay. So, first method 1, that is resolution of forces. Okay. Now, to know this, we should know, first of all, understand what are the forces that are acting on the body. Now, first let us take block A. The block A in this particular system is in contact with the vertical wall or vertical surface. 1 is with the vertical surface, 2 is with the wedge. Now, we can take now one more. Wedges are weightless components. They are weightless component. That means negligible weight. Weightless means negligible weight. So, when you are assuming this one here, we know the motion of the block, it is going upwards. So, we know the frictional force that is acting on this surface, it will be downward direction. Coming to the frictional forces on this contact surface depends upon the motion of the wedge. As the wedge is moving towards right, the frictional force on the wedge at the top and at the bottom will be in leftward direction. So, for equilibrium condition, the frictional force on the block at the contact surface will be opposite to the wedge frictional forces. That means they can be in this direction. And the normal reactions are also equivalent opposite to each other. Okay. Now, knowing this, let me first go for the block A. The block A is like this. The weight component acting here, W. There is no contact here or no force here, so this edge is free. This edge is in contact with the vertical surface, so let me call this as N1 normal. Since the motion is in upward direction, the frictional force here would be mu N1. Agreed? Right. Now, the next thing is this force. In this force, draw a normal reaction which is perpendicular to this surface. I call it as N2. Now, you should know whether the frictional force is in right direction, left direction or right direction, isn't it? As I said, based on the wedge motion, you have to represent the frictional force. Since the wedge is moving this way, the frictional forces on the wedge caused because of the block and the ground surface will be leftward. So, the frictional force on the block now would be opposite to this force, that is towards right. So, the frictional forces are mu and 2. If you know, this is block A. Agreed. Now, you should resolve them to one particular plane. Let me say I shall resolve this into this direction and in this direction. So, this becomes theta and this becomes theta. So, let me put everything in y and x plane, xy plane. So, this is x plane, this is y plane, xy plane. So, I have w here, downward direction, mu n1 also in downward direction, n1 towards right. Okay. Now, resolve these forces. Once you resolve these forces, they can be mu n2 cos theta and mu n2 sin theta. Similarly, if I resolve this can be n2 cos theta and this is n2 sin theta. So, negative n2 sin theta and mu n2 cos theta sin theta, mu n2 cos theta. Downward direction is mu n2 sin theta, then upward direction here is n2 cos theta. Right? Now, just apply the equilibrium forces. Sigma fx equal to 0 plus n2 sin theta minus n1 plus mu n2 cos theta equal to 0, equation number 1. Then sigma fy equal to 0 is plus n2 cos theta minus n1 mu n1 minus w minus mu n2 sin theta equal to 0. So, these are the two equations. From here, sometimes the mu value here can be different from here. That means, as I already mentioned, the coefficient of friction depends upon the materials that are in contact with each other. This can be a steel block and this can be a concrete wall. This can be a wooden wedge and steel block. So, the coefficient of friction here can be different, coefficient of friction here can be different, and even coefficient of friction can be different. Now, in this case we are assuming that the mu value is same everywhere. So, I am putting it. Otherwise, you need to be indicating the different coefficient of friction values also in the equations. Okay. So, from here you need to calculate what is more important is n2. N2 you need to calculate. Okay. Because that n2 again we are going to use here at the wedge friction values. Now, let me do for wedge. The wedge problem goes this way, forces on the wedge. Okay. This is theta. This is the force P. As this is the force P and the motion is in this direction, the frictional force mu n2 is equal and opposite in direction. Okay. Mu n2 here is in right direction on the block, mu n2 on the wedge is opposite to this, okay, upward direction. Then comes your n2 which is 90 degrees here, and there is one more normal n3 and mu n3. So, these are the forces that are acting on the wedge. These are due to the ground surface onto the wedge. Now, if you resolve these forces again, if this is theta, this is again theta. So, this becomes n2 cos theta, this becomes n2 sin theta, and this becomes mu n2 cos theta and this becomes mu n2 sin theta. So put them again in x axis and y axis, all the forces. This is x, y forces. Upwards is n3. This is mu n3. Again this is p. Then this is mu n2 cos theta. Upward is mu n2 sin theta. But downward direction is n2 cos theta. N2 cos theta. And again this left n2 sin theta. So I have placed all the forces on xy plane. So now calculate again sigma fx equal to 0. Sigma fx equal to 0 is minus mu n3 minus mu n2 cos theta minus n2 sin theta plus p equal to 0. Then again sigma fy equal to 0 equation. I call this equation number 3. Then sigma fy equal to 0. Now n3 plus mu n2 sin theta minus n2 cos theta equal to 0. This is equation number 4. So once you get n2, substitute to the n2 here and then derive the value of p. How much force is required? What does the p tell you? How much force is required to be applied on the wedge to raise the weight to a certain height? So this is useful for us to determine how much p is required. Now let us understand the same problem in a different method. That is the alternate solution. Now this is method 2, which is vector method, mostly based on the total reaction of frictional force. Okay, I call it as a vector method. Okay, now in this, let us first take the block. Now on the block, suppose this is the block. You have weight W. Okay, then you consider the reaction that is caused, resultant reaction. I call it as R2, which it is at an angle of phi. We have already discussed that when a body is placed on a surface and is pulled with a force, and the weight is acting downwards, you have normal reaction and frictional reaction. Okay, frictional action. Now we can replace this F and N with R, which is at an angle of phi with N. So this R is called the resultant of frictional force and the normal reaction. So I am using now R2, which acting at an angle phi with the normal reaction, whereas your frictional force will be in this direction, normal reaction in this direction. The resultant of these two would be R2. So I am just replacing those two with R2, right? Then similarly, if you have this normal value here this way, and I can always say this also, then I can represent the resultant of this, call it as R1. R1 again is at an angle of phi with the normal reaction, and again theta with this vertical direction, Now let us, since we have three forces, vectors, let us represent those three in a vector diagram. Now let us represent the three forces in a vector method, which goes this way. W acting downward direction, your R1 in upward direction, and then R2 in this direction. So this is R1, this is R2, right? Now what is important is we need to represent the angles. The angle between W and R1 is theta plus phi. So I show this as theta plus phi. Then the angle between R2 and W, here this is 90 and this is phi. With the horizontal it is phi, right? So suppose W here, if you imagine W here, this is 90 and this is phi, 90 plus phi. So this is an unknown angle. Let me call it as alpha, where alpha you can calculate as the sum of the angles of a triangle 180 minus theta plus phi plus phi. Okay, so that you can obtain alpha from this equation. Now you need to, since you have three forces and a closed vector diagram, apply the sign rule. Apply sign rule to determine the unknown. Now what do you mean by sign rule? Sign rule is the ratio of force vector to sine of opposite angle. That means, let me take first this vector R2. So R2 divided by sine of the opposite angle. Sine of the opposite angle, that is sine theta plus phi. Next R1, that is equal to R1 divided by sine 90 plus phi. The opposite angle is 90 plus phi. That is equal to RW divided by sine alpha. So the unknown alpha or R1 and R2 can be obtained by taking any two equations, relations, and solve the problems for unknown values. So this is how you can solve the values of reactions from the vector method. This is for the block. Now let us solve for wedge. Now the wedge is this way. This is the force P. Then you have the resultant total reaction on this, let me call R2, which is making phi here, upward direction, right? Then you have, let me say, the same R1, okay, R1. So this with the normal and with this, I call it as phi with this and theta with this, knowing that this is theta. Now draw the vector diagram for this. For this, the vector diagram goes this way. This is P, this is R2, R2 with P. That means P is this way, right? R2 is with this phi, so this becomes 90 minus phi. Then comes R1. The angle between R1 and P, that means if you say this, the total is 90, 90 minus theta plus phi. 90 minus theta plus phi. And this is an unknown angle beta. Now apply the sine rule to this problem. The sine rule goes like this. P divided by sine beta equal to R2 divided by sine of 90 minus theta plus phi, that is equal to R1 divided by sine of 90 minus phi. So, these are the ratios. Now, use any two ratios to get the unknowns. Thereby, you can solve the p value, that is the required applied force on the wedge to raise the body to a certain height. So, you can either follow a resolution of forces method or a vector method. Okay. This can be used only if you have 3 forces in the system. If you have more than 3 forces, then it is better to use resolution of forces.
Let's understand the concept of the wedge using a problem. The problem is, a block weighing 1000 Newton is to be raised against a surface inclined at 60 degree to the horizontal by means of 15-degree wedge. Find the horizontal force P, which will just start the block to move if the coefficient of friction between all the surfaces of contact be 0.2. Assume the wedge to be a negligible weight. Now let's understand the problem. The problem says that there is a block as shown in the figure, which is of 1000 Newton and is inclined onto a surface which has an inclination of 60 degree to the horizontal, and it is being raised upwards by means of a wedge. This part is a wedge, which is an angle of 15 degrees to the horizontal. Now the question is, find this horizontal force P required to be pushed in leftward direction so that the block 1000 Newton will just start moving up. Another information that is being given is the coefficient of friction between all the contact surfaces is 0.2. So, what are the contact surfaces? One is the inclined surface and the block. The second one is the block and the wedge contact surface. And the third one is the wedge with the horizontal surface. So, we have 3 contact surfaces and the coefficient of friction is 0.2 as to be assumed. Now, to solve this problem, we need to draw free body diagrams. Now, in this case, we consider 2 free body diagrams separately. One is representation of forces on the block, and the second one is the representation of forces on the wedge. Now, first let's go for the block. The block has a weight of 1000 Newton represented in downward direction perpendicular to the ground. Then this edge of the block is resting against the inclined surface 60 degrees. So, the surface will be creating a reaction force on the block and represented as N1. And another force is the frictional force. Since the block is moving up, as the P here pushes the wedge in leftward direction, the block has to raise upward direction, right? So, since the block is moving in upward direction, the friction here will be represented in downward direction. So your mu N1 is represented in downward direction. Now coming to the contact surface of the block and the wedge, this portion. In this portion, the wedge creates a reaction force onto the block that will termed as N2. So your N2, which is the reaction developed by the wedge onto the block, which is perpendicular to the contact surface, is represented in this direction, N2. Now, since the wedge is moving in leftward direction, the friction force on the wedge will be in upward direction, and the frictional force on the block will be quite opposite to that on the wedge. Therefore, the frictional force on the wedge will be in downward direction. So mu N2 is shown in downward direction. I repeat this point. The wedge is moved in leftward direction by applied force P. Then the frictional forces that are acting on the edge will be in upward direction. Then the frictional force acting on the block will be equal in magnitude but opposite in direction at the contact surface of block. That means in downward direction. So your mu N2 is represented in downward direction. So now that you have all the forces and reactions acting on the block, you need to resolve these forces onto XY plane. So let us consider the horizontal as X and the vertical as Y axis. Now coming back to the reaction N1 caused by the wall onto the block is at an angle of 30 degrees with the horizontal. Then you resolve this component. This becomes N1 cos 30 and this one becomes N1 sin 30. Okay. Then mu N1, which is again at an angle of 30 degrees to the horizontal, is resolved to mu N1 sin 30 and mu N1 cos 30. Then coming to the reaction by the wedge onto the block, N2 is at an angle of 15 degree to the vertical line. So you resolve this N2 as N2 cos 15, N2 sin 15. Then mu N2 at an angle of 15 degrees to the horizontal will give you mu N2 cos 15 and mu N2 sin 15. Now putting all these forces onto XY plane, you have X axis and Y axis in XY plane, and apply the equilibrium equations for this. That is, sigma fx is equal to 0. So sum of the forces on X axis is equal to 0. So you take forces towards rightward direction and forces to the leftward direction. Similarly, sigma fy equal to 0. The sum of the forces on Y axis are also equal to 0. So the next free body diagram would be about the wedge. So these are the equilibrium equations for the block. So you can solve these equations and get some unknown values, that is N1, N2 reactions. Going to the wedge. So this is the wedge. So the wedge is a weightless component. So you don't have to represent any weight on this. You have applied force P acting towards left direction. Now since the applied force is in the left direction, the frictional forces will be acting towards right. So this is the ground surface having N3 as the reaction developed by the ground onto the wedge and perpendicular to the surface. Your mu N3 is towards right because the wedge is moving towards left. So similarly, N2 is now the reaction caused by the block onto the wedge N2. And this N2 is now again perpendicular to the wedge top surface. So mu N2 now will be opposite to the direction of that developed on the block, which was downwards, right? Now this is now in upward direction. Mu N2 is in upward direction. Now again, resolve all the forces to x and y axis based upon the angle of inclinations. Now N2 is 15 degrees with the vertical. See, all this is simple trigonometry. You just have to place the angles. Mu N2 is 15 degrees with the horizontal. So when you resolve to mu N2 cos 15, mu N2 sin 15. Similarly here N2 cos 15 and N2 sin 15. Put all these forces of reactions and external forces onto an xy plane this way and apply equilibrium conditions of sigma fx equal to 0 and sigma fy equal to 0. So let's go back to the equilibrium equations for the wedges of sigma fx equal to 0. So sum of the forces in x direction equal to 0 and sum of the forces in y direction also equal to 0. Solve these equations 1, 2 of block and 3, 4 of wedge and then determine the value of P, which is 595 newtons. That means to raise a block of 1000 Newton in upward direction through wedge, you need a force of 595 newtons. So with less effort, you are doing more work. So wedges are also considered as a simple machine. Let's understand the application of a wedge as a wood splitter. The problem is a wedge is used to split logs. If phi is the angle of friction between the wedge and the log, determine the maximum angle 2 alpha of the wedge so that it will remain embedded in the log. So it says that there is a wooden log and that wooden log has to be split into 2 parts using a wedge. Wedge is usually a tapered component with an included angle of 2 alpha and an applied force P acting vertically downwards on the wedge splits the wood into 2 parts. So the question here is, determine the maximum angle 2 alpha of the wedge so that it will remain embedded in the log. So this problem has to be solved in 2 stages. In the first stage, you determine the applied force P if the reaction is a known value. In the second stage, the wedge has to be driven and the force is removed to determine the angle alpha. So let us start with the first phase of the problem. In the first phase, consider the free body diagram of the wedge. Remove the wooden logs. In place of the wood, you apply the reaction forces acting on the wedge by the wood on either sides. So if this is the wooden log, You just extend this part as a triangle and the included angle as 2 alpha. If P is the vertical load acting downwards, then R1 and R2 are the total reaction force acting on the each edges of the wedge. For example, R1 now is the reaction of N1 and mu N1. N1 is, suppose this one, normal reaction of the wood on right side onto the wedge, and mu N1 will be in upward direction because P is moving, allowing the wedge to move in downward direction. So the resultant of N1 and the mu N1 is R1. I am considering this R1 acting on this edge at an angle of phi, which is a friction angle to the normal reaction N1. This in turn is at an angle of alpha to the horizontal. This is simple trigonometry and geometry. Then comes your R2, the similar thing, which is the total reaction force of N2 and mu N2, which is acting in upward direction. This R2 is acting at an angle of phi with N2, an angle of alpha with the horizontal. Now knowing these forces, that means R2, R1 and P, resolve these forces to the x-axis and y-axis and then apply the equilibrium equations. For instance, when I resolve these two forces, R1 becomes R1 cos alpha plus phi, the horizontal, and R1 sin alpha plus phi, vertical. This R2 now becomes R2 cos alpha plus phi on horizontal and R2 sin phi plus alpha in the vertical direction. So in sigma fx equal to 0, you have two forces. One is R1 cos alpha plus phi and R2 sin cos alpha plus phi, which are acting in opposite direction to each other. So here R1 is equal to R2. Now apply sigma ffy equal to 0, in which the vertical, sum of the vertical forces are equal to 0. In this case, it is R1 sin alpha plus phi, and in this case R2 sin alpha plus phi, both are in the same direction, upward direction, minus P, downward direction, equal to 0. So using these two equations, you are able to find the applied force P is equal to 2R1 sin alpha plus phi. So P is the function of friction angle, wedge angle and the reaction force. Now getting into the second part of the problem. Here, consider the free body diagram of the wedge without applying P. Now this becomes when the wedge has been driven inside the wooden log and the force P is removed. The wedge now tries to split out. So the direction is reversed. Also, that means no force P acting on the wedge. Now in this case, your R2 is making an angle of alpha with the horizontal and R1 is making an angle of alpha with the horizontal. So sigma resolve these two forces again to x-axis and y-axis as R2 into cos alpha minus pi in here and R1 into cos alpha minus pi in this direction. Since both are in opposite direction, the sum is equal to 0 here. So here again R1 is equal to R2. Now resolving the forces in bidirection, you have R1 sine alpha minus phi in vertically upward direction, R2 sine alpha minus pi in vertical direction. Both these two forces are in upward direction. Then their sum is equal to 0 here. Then you have 2, since R1 is equal to R2, 2R1 into sine alpha minus pi equal to 0. So alpha is equal to pi. That means when the wedge angle is equal to the frictional angle, that's the maximum angle of the wedge, so that it will remain embedded in the log.
Now let us understand the mechanism of power screws. A power screw is a machine element which is used to convert a rotary motion into uniform longitudinal motion. It is basically used in screw jacks, valves, presses, tensile testing machines and machine tools. So let us now understand in detail exactly the working principle of these power screws. The power screw actually assembly comprises of a screw, that means a threaded rod on which the threads are cut externally. Basically the threads are of square shape or acme profiles. So these are the externally threaded rod. Then the next important element in a power screws are nut. The nut will have internal threading, either square thread or acme threads. So the reason to choose these type of threads is because the power screws are such elements which has the capacity to handle higher loads. Sometimes the loads are in tons. So that's the reason you opt for square thread or acme threads. Then this is the collar on which this entire thing is supported. Okay, now if F is the load in tons, external load that is acting on the screw may move up or down based on the rotary motion that you give to the nut. So what exactly is happening in between the screw and the nut? Suppose, as I said, the screw is a cylindrical rod on which the threads are machined, either square thread or acme thread. Then a nut is another machine element in which these same similar type of threads are internally machined. So it has an internal threading, this has an external threading. Now this is inserted inside this screw, and when the nut is rotated, it slides on the screw, either upward direction or downward direction. If you rotate the nut in a clockwise, it may move in upward direction. Now let us understand what exactly happens in the interface between the nut and the screw. When the nut is rotated in clockwise direction, the nut moves in upward direction. When the nut is rotated in the anti-clockwise direction, then it moves in downward direction. Since the nut has internal threads, those internal threads are now in contact with the external threads of the screw and take the path. The path taken by the nut while moving up or down is a helical path. Now let us understand the mechanism of a screw. The screw is imagined as a cylindrical rod on which the threads are cut like this. This is the thread that goes this way and again this way and again this way, right? And it makes an helical angle alpha. Now this, since is the cylinder, the diameter is dm and this is the length L. Now when you cut this cylinder for a development and open the cylinder, it becomes a rectangle. The length remains the same for the rectangle, but the width is now nothing but the circumference of the circle because it's a cylinder. Now when you draw that, this is a development of the single thread screw whose width becomes pi dm. That's the circumference of a circle and the length remains same. In this, if you just trace the path of the thread, helical thread, then it looks like an inclined line. Now, if this is the nut holding the load, external load 4F, which can be in tons, and this is a screw which has a helix angle alpha, and L is the distance between the first thread and the second thread. That means this portion to this portion. I am calling it as L. L is nothing but lead. Lead is the distance travelled by the screw for one revolution. The distance, once you rotate this screw, the distance travelled by the path from this point to this point is what is called lead. Sometimes the lead is 1 into P, it is called single thread. This is how you represent a single thread. Sometimes it can be 2 times P, that is double thread. Double thread is, it has threads here and here. And sometimes it can be 3 times P, it is triple thread. So these are called, I represent as N into P, multi-threaded screws, multi-threaded screws. Based upon the load that we need to carry, the multi-threadeds are used in the applications, right? Now, let us clearly understand one screw jack mechanism and then try to go into the mechanics part of this. So as I said, the power screw or a application as a screw jack will comprise of a screw thread. This is a screw rod and this is the threading part. This is the threading part, internal line that I have given, which is having a diameter of dm. This is the nut. Assume that it is fixed. Then you have a cup-like arrangement so that you can place the load that can be in tons, can be placed here. Now the objective is to raise this load up or down. This happens by rotating the screw. To rotate the screw, you have this arrangement of a handle and then you apply Q, an external force, so that it creates a torque Q into A, where A is the length of the handle arm. Now that torque, which is an external force or action done on the screw, will create a reaction by creating a force P at a distance of Rm, that is the mean radius. So P is nothing but a reaction exerted on the screw at a radius Rm, right? Now, basically there are two phenomena that are happening in this screw jack. One is the load is rising up. The next one is the load is sliding down. Now let us take the first case, that is case 1. As I already mentioned that this forms a wedge problem. This motion of the nut on the screw in a helical path is similar to a wedge problem. Is similar to a wedge problem. So we will directly consider a wedge here. This is first thread, this is a second thread, and the distance between the thread can be the lead. Then place the load on this, okay, and alpha is a helix angle, and this is nothing but pi dm. That is the circumference of the thread wound on the cylinder. Then what are the forces that are acting on the body? In the first case, let us take the body moving upwards. Body moving upwards. That means the motion is in upwards. In this case, as you know, the force is always acting perpendicular to the ground surface. Then there is a frictional force and normal reaction. So normal reaction acting perpendicular to the inclined surface. Since the body is moving up, I take mu n in downward direction. In addition to this, you need to represent P, the force acting on the thread because of the torque that is acting on the screw. So that force is acting this way. So now you have actually here two axes. I can say y dash and x dash. Now if you just again put them in the axis in this way, x dash and y dash. This is the force F at an angle alpha. And this is a P, you can put this P here at an angle alpha here, and mu n is on the same axis, and also n acting on the same axis. So these are the four forces that are acting on the load. Now you resolve these forces. This happens F cos alpha and F sin alpha, and this resolution is P cos alpha, P sin alpha. That's it. Now your sigma Fx equal to 0, equilibrium conditions. So the sum of the forces acting in x direction are 0. I take mu n minus F sin alpha minus P cos alpha equal to 0. Then sigma Fy equal to 0. Then in this case F cos alpha minus n minus P sin alpha equal to 0. Now consider mu n as tan phi, where phi is called the friction angle. So solving these two equations, you get a relation P equal to F tan phi plus alpha. So this is the expression is important to know the torque required by the effort that you need to apply on the screw to raise the load in upward direction. So P is the external force, or that is the effort that we give. F is the main load that it needs to carry, to lift or to slide down, into tan of phi friction angle, alpha thread angle. So this is case 1. Now let us understand case 2. In case 2, the similar thing, but the direction of the friction is in upward direction because the body is moving downward direction. Okay? And so the frictional force is in upward direction, and the force P is again in the similar direction with N. And you do the same exercise on this, resolve all the forces to one axis, and then solve the equilibrium equations to obtain P is equal to F tan phi minus alpha. So this much amount of force is required to lower the load on the through the screw, to lower the load through the screw. So these two has to be noted. The next aspect in power screws is the overhauling and self locking of screws. See, let us understand first what is overhauling. Now, if you know the torque required to lower the load, that is, as we have just recall, this is a screw, this is the nut, screw and thread, and once you rotate the screw, the load may rise or lower. So the torque required as I said can be in terms of force, that is the weight of the load, is expressed as F into dm by 2. The dm by 2 is half the radius into tan phi minus alpha. If considering these two angles, where phi is the friction angle and alpha is the helix angle of the thread or screw angle, if phi is greater than alpha, obviously the torque is negative. This is also known as back driving screws. Now what happens in this is, this load will start moving down without the application of any torque. It just continuously keep moving down, sliding. Now here effort should be given to the screw to resist the tendency of the load to descend. So that is what is called as overhauling, or otherwise back driving screw. This happens when the frictional angle is less than the helix angle. The next phenomenon is self-locking, that is vice versa of to this. If phi is greater than alpha, the friction angle is equal to or greater than the helix angle, here the torque becomes positive because this is more than this. The torque is positive. In this, the screw remain stationary and effort is required or applied to lower the load. So these are the two important mechanisms of a power screw which are used mostly in many applications.
So let's understand an application of a power screw. A very simple application. This is a C clamp. This is this power screw. This part is the nut part which has internal threaded, and this part is a movable part. It translates as you rotate this handle. Then this is a fixed part of the clamp. you place any component in between the movable and fixed frame, and once you rotate the screw, it translates into linear motion and holds the clamp tightly. So let's see the problem. A clamp of double threaded screw. So this screw here is not a single thread, it's a double threaded screw. Has a diameter of 10 mm. The screw diameter is 10 mm. The friction is 0.3. The friction between the nut and the screw is 0.3. If torque is 40 Newton meter is applied in tightening the clamp. So this part, when you rotate, that is about 40 Newton meter. Then, as I said, the movable frame will tighten the wood. The force is exerted on the wood. So, question is, determine the force exerted on the wood. A. And B is the torque required to loosen the clamp. So there are two questions in this particular problem. So let's solve the problem. Considering first the force exerted on the wood. That means when you rotate this handle, the movable frame will exert the force on the wood and tighten it. So what is that force that is applied on it? So we'll see what is whatever given data to us. One is lead. Lead is 2 times P because it is a double threaded part. So the P is nothing but pitch. So you can assume the value of pitch if it's not given. Pitch can be 2 mm. So 2 times of P, 4 mm. Then comes your tan theta, which is nothing but L by pi d. L is the lead by circumference pi d. So you are getting angle theta as, this is a wedge angle. Theta here is wedge angle, 7.3 degrees. Okay, let's go back to the working mechanism of this. As we know that the nut and the power screw of this part is considered as a wedge with a block. So you can consider that as a wedge with a block having a weight of W. The block of weight of W. Here we are saying that W is the force that is exerted on the wood. Now on this, in the first case, the force is exerted on the wood is treated as motion impending up the plane. So you are creating a motion moving the block in upward direction. So when the block is moving upward direction, the frictional force will be acting in downward direction. So here we consider resultant reaction of N and mu N, that is R, which is acting at an angle of theta plus phi, where theta is the wedge angle. So you need to determine Q. As we know that one edge of this wedge is lead and the base is nothing but the pi d, that is circumference of the rod, screw rod. Now coming back to the calculations, we know that the wedge angle is 7.3 degrees. So mu s frictional coefficient is 0.3. So the angle tan phi is equal to mu s is calculated as 16.7 degree. Then you have Q into R is equal to torque, 40 Newton meter. Now Q is nothing but the resistance force offered on the thread due to the applied torque, that multiplied by the radius of the screw rod equal to 40. So then you get Q is equal to 8 kilonewton since R is equal to 5 mm. D is 10 mm is R is 5 mm. You got Q as 8 kilonewton. Now coming to this vector diagram. This vector diagram, triangle vector diagram, is drawn based on W, Q because you are moving it upwards, and R. Right? So Q as 8 kilonewton is the only known value. What you need to determine is W. What is the force that is exerted on the wood? Now since we consider this as the wedge problem on which the motion is impending in upward direction, we use the expression W is equal to Q divided by tan theta plus phi s, where theta is the wedge angle, phi s is the frictional angle. And you substitute this value. The value is 17.97 kilonewtons. Coming to the question B, it is the torque required to loosen the clamp. That means rotate the handle in anti-clockwise direction so that the mobile frame moves towards right and loosen the wood. For that, you can directly use this wedge and block problem with motion impending down the plane. So here I am applying the force Q downward direction, and the W and R accordingly to the motion of the block. So using the expression of motion impending in downward direction, Q is equal to W tan phi s minus theta. So we already know that W is 17.97 and apply all these values, you are getting Q as 2.975 kilonewton. So torque is Q into R, that is 14.87 Newton meter. That means what you understand here is 40 Newton meter is applied to tighten the clamp and 14.87 Newton meter is applied to loosen the clamp. Okay. Here phi s is greater than theta. Since this is happening, the screw is self-locking.
Now let us understand the concept of connected bodies. The connected bodies majorly has three major components. One is suppose block A, which is of 400 kg, block B of 200 kg. So two heavy objects are connected with another heavy object which is of 100 kg weight. Call it as strut. So strut is basically a multi-force member which is pin jointed on block A and on block B. So the pins here will develop reaction forces. It happens when a force, applied force P is acting on the body A, the body A moves towards right direction and the body B moves in upward direction. Then the pin here will have reactions of AX, AY, and here it is BX and BY. So these are the reaction forces that are occurring on the pins. So let us solve this problem for the value of P. So first let us draw the free body diagram of strut. As I said, the strut is a multi-force body where the weight of it is acting here downwards let me say WAB, which is 100 kg, and the BX in this direction, BY vertically opposite, AX opposite to BX, then comes your AY. So, when you apply the equilibrium equations, sigma Fx here equal to 0, your AX reaction force in x direction is equal to Bx, that is the reaction force at B in x direction. Now, for sigma Fy equal to 0, now let us consider the vertical forces here, that is the weight of the strut lies exactly at the midpoint of the length of the strut. So, the length of the strut is immaterial for us. So, we can consider sigma Fy equal to 0 for Ay equal to By, which is equal to WAB by 2, which is 100 by 2, that is 50 kgs. So, this weight is now distributed at the pins as W by 2 and W by 2. Now, knowing these values, let us go for the free body diagrams of first inclined surface. Now, once you draw the free body diagram for the inclined surface where the object is moving in upward direction, the motion is in upward direction. The weights that are acting on this are, one is the self weight 200 plus the weight of the strut, which is 50. So, totally 250 vertical weight is acting on the body. Next one is the reaction Bx, the reaction Bx in this direction. Now, this slope is 45 degrees with the horizontal line. Okay. Now, let us draw the normal reaction. Let me say NB. Now, since the body is moving up, your frictional force will be in downward direction, mu NB. Right? Now, let us resolve the forces onto this plane or on this plane. Okay. So, let me resolve that everything into this vertical plane. So, this is 45 degrees. I call this as NB sin 45, NB cos 45. Now, this itself is again mu NB, this is 45, cos 45, mu NB sin 45. Now, this angle with this is again 45. So, this becomes Bx cos 45 and this is Bx sin 45. So, these are the forces that are acting on the object which is having 200 kg weight. So, again write down the equilibrium equation, sigma Fx equal to 0. So, my axis is here, this and this is the axis. Okay. So, sigma Fx equal to 0, let me start from here, that is minus mu NB cos 45, this one plus Bx sin 45 minus NB sin 45. Okay. Let me round off whatever that we have completed. This is over. this is over and this is over, is equal to 0. Now let us go for the next equilibrium condition, sigma Fy equal to 0. These two put together, that is minus 250 plus Bx cos 45, sorry, plus Nb cos 45 minus mu Nb sin 45 equal to 0. This is equation number 2. So from here you have two unknowns, one is Nb, another one is Bx to solve. So let us go for the next free body diagram, that is the block A. The block A here is on a horizontal plane where the P is acting in this direction. So the friction here acts in mu Na in opposite to its motion, and this is Na. We know that motion is in this direction. Okay. Then you have the weight of the object, that is 400 plus 50. Right. Then you have B or Ay, which is equal to Bx. Ax equal to Bx. You can either use Ax or Bx. Now the angle subtended with this is 30 degrees. So we call this as 30 degrees. This is a very simple system of forces. So you just resolve this into horizontal, Bx cos 30 and Bx sin 30. Right? Then apply the forces here as sigma Fx equal to 0. This one plus P minus Bx cos 30 minus mu Na equal to 0. This is equation number 3. Then sigma Fy equal to 0. 450, that is minus Bx sin 30 plus Na equal to 0. So equation 4. So after solving all the simultaneous equations, you calculate the unknown P, which is the applied force on block A. The P now comes around 397 kg. So the force of 397 kg is applied on block A, which is of 400 kg, to push 200 kg upwards on an inclined surface. So that's how you solve a connected problem.
Now let's look at problem number 13. A uniform bar AB, 10 meters long and weighs 300 Newton, is hinged at B and rests upon a 500 Newton block at A, as shown in the figure. If the coefficient of friction at all contact surfaces is 0.4, that means here as well as here it is 0.4, then find the horizontal force P required to start moving the block of 500 Newton. The impending motion of the block is towards right and the frictional force resists the motion, hence it acts towards left on the block. So the solution for this is also available in the notes provided in the description link. Let's go to the next application, ladder. Many a times we come across the uses of ladder for attending the higher heights. We observe that care is taken to place the ladder at an appropriate angle with respect to the ground and the wall. We try to adjust the friction offered by the ground and the wall in contact with the ladder. The forces acting on ladder are normal reactions, frictional forces between the ground and the wall and the ladder. Weight of the ladder, weight of the man climbing the ladder also is considered. Considering the free body diagram of ladder, we get general force system. Simplification of the system by considering equilibrium condition can be worked out by following equations. That is sigma fx equal to 0, sigma fy equal to 0 and sigma m is equal to 0.
Okay, now let's solve problem number 14, a ladder problem. Now imagine a ladder is resting on two surfaces. One is wall, vertical surface at point B, and the ground surface at point B. Now this ladder is having a weight of 100 newtons and the length of 5 meters. Imagine a man is climbing the ladder. This is the man climbing the ladder which is inclined at an angle of 60 degrees to the ground surface. Now the question is, how much distance up along the ladder a man weighing 600 Newton can ascend without causing it to slip? So the ladder should not slip while the man is climbing up, is what is to be understood. Now, what we need to say is, let us assume that distance he climbed it to D till such time the ladder isn't slipping. Now, the weight of the ladder, 100 Newton, is placed exactly at the center of the span length, that is around 2.5 meters. Now let us draw the free body diagram for the ladder. Now this ladder is having a weight of 100 newtons at a span, which is having a span length of 5 meters, and this is around 2.5 meters. And we also know that there is a person of weighing 600 newtons at a distance of D from the ground, B point, or let me put the B point here above and A point here. Now, when the ladder is slipping, that means the ladder slides in this direction on the ground and downward direction on the vertical surface. Now, based on this motion direction, we can represent the frictional resistance. So, here at the ground, since it is moving in rightward direction, the frictional force will be in left direction, mu NB, and the normal reaction would be NB. Now, here because it moves downwards, the frictional force would be mu NA and normal reaction as NA. Right? Now, with this motion, Let us now calculate. Our interest is to find out the distance d. Applying the equilibrium of motion, sigma fx is equal to 0, I have Na is equal to mu nb is one equation. Sigma Fy equal to 0, vertical forces 100 plus 600 is equal to Nb plus mu Na. The mu here as well as here are same. Then you need to understand the angles moment at B, that is sigma mb equal to 0. Now taking this triangle formed by the ladder and the vertical faces 60 and this is 5 meters. So 5 cos 60 degrees and 5 sin 60 degrees are the distances of adjacent and opposite sides, right? Now take moment about B. What are the forces that are contributing to the moment? Na will contribute, mu Na will contribute, 100 will contribute, 600 will contribute, whereas these two does not contribute because they are lying on the moment center. Now let us take Na. Na is in this direction, the moment center at this point rotates in this clockwise. So I write it as plus Na multiplied the perpendicular distance is 5 sin 60. Mu Na, which is vertical in upward direction, rotating towards the moment center, that is this one, is again clockwise, saying mu Na multiplied by the perpendicular distance of this, that is 5 cos 60. Then comes another triangle for you. Another triangle here is around 2.5, same 60 degrees. So this forms 2.5 cos sin 60 and 2.5 cos 60, right? So 100, the weight of the ladder rotating about this moment center in anti-clockwise direction. So minus 100 into the perpendicular distance 2.5 cos 60. Then 600 rotated about moment center again in anti-clockwise direction, minus 600 multiplied by this distance, which happens to be d cos 60 into d cos 60 is equal to 0. So you have 3 equations. So after you solve these 3 simultaneous equations, you get the distance the human being climbed on the ladder to be d is 2.034 meters. So after he climbs not even more half of the ladder, that means at a distance of 2.034 meters, the ladder starts slipping, impending motion. Okay. So this is how you need to solve the ladder problems.
Let's move to the next application, belt friction. The belt or rope is wrapped around the pulley to transmit power or effectively used for braking systems. To evaluate the effectiveness of the system, the tensions in the belt or rope are of importance. So consider this as a driver pulley and this is a driven pulley or otherwise called follower pulley. And the belt slips around the pulley from tight side to slack side, causing two different tensions, T1 and T2. So this is a schematic diagram of a pulley and the belt wrapped over the pulley, having two different tensions, T1 and T2. Let the belt wrapped over the pulley be theta, and d theta is the small elemental segment of belt in contact with the pulley, and m is the rotational movement caused on the pulley.
Now, let us understand the mechanics of belt friction. Belt is a mechanical element used for power transmission. Now, consider two pulleys of different diameters, one being the driver pulley, the other being the driven pulley. The motor source, that is like an electric motor, is connected at this point, and the power is transmitted to the driver pulley through the motor. Now, when the driver pulley is made to rotate, the belt that is wrapped around the two pulleys rolls such a way that the driven pulley is rotated. So, here the friction that is acting at the contact surface of the belt and the pulleys becomes the driving force for power transmission. Now, since the belt is wrapped around the two pulleys, the belt will be noticing two types of tensions because of one being tight side, the other one being slack side. And there is another important point to be noticed is the wrap angle of the belt on the pulleys. Let me call it as beta. Now, coming into the details of this frictional force movement on the belt. Let me take a small part of the belt. This is the belt, and one side as tight side, I call it as T2, and slack side as T1. The difference of these tensions will transmit the power. The frictional force, which is at the contact surface of the pulley and the belt, will be acting in the opposite direction. Right? Now, let me take a small elemental strip of this belt in this way. This forms the elemental strip with an included angle of d theta. Right? Now, since the frictional force is moving in this direction, I represent it as dF. Now, dN is the normal reaction force caused by the pulley onto the belt. Then the tensions are represented at the cut section of the belt, one T, that is slack side, T plus delta T on the tight side. If this is d theta, the angle subtended by the surface with this tension force is d theta by 2, and again with T plus delta T with the surface of the belt as d theta by 2. Now, with these forces on an elemental strip, let us write the equilibrium equations. For that, I will put all of them on x axis and y axis. This is y, this is x. Okay, I will treat this as x axis and this one as y axis. So, on y axis, I have dN x axis I have df, these two. Then I resolve this to t cos d theta by 2 in horizontal direction and t sin d theta by 2 in vertically downward direction. Here it comes as t plus delta t into cos d theta by 2 in the horizontal direction and then t plus delta t into sin d theta by 2 in downward vertical direction. Now, apply the equilibrium equations onto the belt. Sigma fx equal to 0 gives you sum of the forces in this direction positive and in this direction as negative. I call t plus delta t into cos d theta by 2 minus df minus t cos d theta by 2 equal to 0. Let me call it as equation 1. Now, sigma fy equal to 0 gives you dn, forces in this direction positive, in this direction negative. So, plus dn minus t sin d theta by 2 minus t plus delta t into sin d theta by 2 equal to 0. Let me put it as equation 2. Now, assume that cos d theta by 2, a small angle, is equal to 1 and sin d theta by 2 equal to d theta by 2. Substitute these values in the above two equations and solve the equation to get the final dt equal to t into mu into d theta. So, I pull this here, call it as t by t equal to mu d theta. You integrate these two this expression on both sides with this as T1 T2, that is the varying tensions, and this as 0 to beta. Beta is the wrap angle. Okay. Then when you solve this, this comes as logarithmic E T2 by T1 equal to mu beta, or I can call this as T2 by T1 is equal to E into mu beta.
Let's understand the velocity ratio of belt pulley systems. Velocity ratio is defined as the ratio of velocity of the driven to the velocity of the driver. If n1 is the speed of the driver in RPM, d1 is the diameter of the driver, and if n2 is the speed of the driven in RPM, d2 is the diameter of the driven. Here, the length of the belt passing over the two pulleys per minute will be the same. So, you need to note that the linear velocity is constant. So, you call V is equal to R omega. So, omega is pi d n. Here, when this linear velocity is constant or same, you equate pi d1 n1 equal to pi d2 n2. So, that means n1 by n2 is equal to d2 by d1. That means the speeds are inversely proportional to the diameter of the pulleys. The smaller diameter of the pulley will rotate with a high speed, and the bigger diameter of the pulley will rotate with a low speed. So, this is the ratio for the belt pulley system.
Now, let us understand problem number 15. Here, there are two blocks, one is of 2000 Newton and another block unknown weight W is resting on 2000 block, and these two in turn are resting on a inclined surface at an angle of theta. The slope of this is given as tan theta is equal to 3/4. Now, these two blocks in turn are held with a rope passing through a pulley in this way. Now, the question is, determine W to prevent the down plane motion of 2000 Newton, to prevent this motion of this coming in this direction. How much of W has to be placed on the top of this block? A very simple way of solving this problem. You divide this problem into three free body diagrams. The first free body diagram, you consider both the blocks and represent the forces acting on it. Write down the equilibrium equations. And in the second free body diagram, consider only the top block. Represent the forces on it and solve the problem. And the third free body diagram is, consider only the belt pulley element and apply the equilibrium conditions and solve the problem. Now, coming to the first free body diagram, I have taken both the weights, the block 1 W, block 2 2000 on an inclined plane. So, since these two blocks are attached to the ropes which have tensions T2 and T1. So, I consider the tension pulling T2 and T1. Then W plus 2000 is acting in a vertical direction, and N1 is a normal reaction by the inclined phase onto the bodies. Now, our interest is that this should not move down, right. So, there should be a frictional resistance acting in upward direction. Then, in this case, you just have to resolve these forces onto this plane y, y, x, x and solve the problem of this simple W plus 2000 cos theta, and in this W plus 2000 sin theta. So, sigma fx in this case becomes positive sides, this one T1 plus T2 plus minus W plus 2000 sin theta plus mu n1 equal to 0. Sigma fy equal to 0 is W plus 2000 cos theta equal to n1. So, you have two equations. Now, coming to the second free body diagram, where you are considering only the top block. Now, in this, the forces that are acting on this block are the weight of the block, obviously, the tension of the rope, normal reaction exerted by the 2000 Newton onto the W block is upward direction, and the frictional force acting here, I call it as F2, which is in downward direction, mu N2. Now, here the equilibrium condition sigma fx equal to 0 goes as this as W cos theta and this as W sin theta. So, it is plus T2 minus W sin theta minus mu N2 equal to 0, equation number 3. Then W cos theta is equal to N2 is equation number 4. Then coming to the free body diagram, 3, you have pulley and belts acting this way, and the equation here goes as T to tight side by slack side equal to e to the power of mu beta, where beta is the wrap angle. Since it is touching in 180 degrees, so take them in radians, pi radians. So you have T2 is equal to T1 into e to the power of mu beta. Mu is a given value which it goes around 0.3 and beta is pi radians. So you get a relation between T2 and T1. Those relations you substitute here, and theta is already known as 3, tan theta is 3 by 4, you substitute, you are going to get W, which is around 273 newtons. So you apply a weight of 273 newtons on the top of 2000 newton, so that you can prevent the down plane motion of 2000 newton body. Okay, let us discuss problem number 17, an interesting practical problem. Now we have this a braking mechanism in which there are 3 major components in the system. One is compound pendulum, second one is the hydraulic cylinder, and the third one is the brake lever. Now in the compound pendulum, you have 2 pulleys, a small pulley of radius 400 mm and a bigger pulley of radius 600 mm, which have concentric, means have the same center of rotation. So this is a compound pulley, and a weight of 2000 newtons is hanging on a small pulley. So the small pulley rotates about B in counterclockwise direction. Now a brake lever is attached here, where the brake pad comes in contact with the compound pulley, and the lever on the other side is hinged at point A. This is the hydraulic system, where the cylinder and the piston hydraulically operated. The piston moves down on the lever to arrest this motion of the pulley. So the question is, how much force is required for this system to arrest the motion of the pulley through the pad, brake pad? So when a force is applied in this direction, then the brake pad will apply force on the pulley, resisting the motion of the pulley. So let us solve this problem in parts. In the first part, we will take this set of pulley and the pad. Now when you are taking the free body diagram of pulley, okay, you have the pulleys here, set of pulleys here with B, and this is the force 2000 newtons in downward direction, and the brake pad exerts force on the pulley, causing the normal reaction on the pulley N. While it is exerting force, the frictional force is caused at the contact surface. That frictional force direction depends on the direction of the rotation. Now since it is rotating in this counterclockwise direction, the frictional force acts in opposite to its motion. So you have 3 forces acting on this pulley. So simply you take sigma MB equal to 0, and in this sigma MB equal to 0, take the moment about B. The force 2000 will contribute to the moment, and force F will contribute to the movement, and N does not contribute to the movement as it is lying on the same axis of the movement center. So, the force 2000 multiplied by this distance, which is 400 mm, and this distance is 600 mm. So, this force 2000, moment about B rotates this direction, which is counterclockwise. So, minus 2000 into 400, and this force towards moving towards B, which is this direction, plus F into 600 equal to 0. Then you have the value of F calculated. Then, but F is equal to mu into N. Mu is given as 0.4 in the problem, that is the coefficient of friction between the contact of the brake pad and the pulley. So, when you substitute, you get the value of N. Agreed. Then, coming to the next free body diagram of a brake lever. Brake lever. Agreed. So, the brake lever, if you draw, you have the normal reactions and frictional force equal in magnitude but opposite in direction. That means the normal reaction on the pulley is in upward direction, then the normal reaction on the brake pad would be in downward direction. And the frictional force in left now will be in right in this brake pad, equal and opposite. Then the force applied here at a distance of 500 mm from the hinge is in upward direction. So, you know that this is 500 mm, this is 1000 mm, and this distance is 100. Simple thing is, apply moment about A. So, here all the three forces will cross moment about A, that is sigma MA equal to 0, F in this direction, moment about A is in this direction, rotating in clockwise, that is plus F into 100, N about movement in this direction, that is minus N into 1500, 100 plus 500. Then P in this direction, that is plus P into 500 equal to 0. Now, since you get the values of N and F from here, substitute those values here and get the value of P. Here the P is around 4860 newtons. So, 486 kg force is required to be applied on the lever at a distance of 500 mm from the hinge so as to arrest the motion of compound pulley through the brake pad.
Let's understand the concept of rolling wheel. Here consider a body rolling without slipping on a surface and let P be the externally applied force. In a rolling wheel, there are two phenomena that happen. One is the wheel rotates about its own center of rotation, and the second one is the wheel moves forward. Okay, so let us consider this as a rolling wheel with O as a center of rotation, and this wheel is affected by the linear acceleration of center of the wheel O and the angular acceleration alpha about O. The point P is the instantaneous center of this wheel, which is actually the contact point of the wheel and the surface. So this wheel, which is rotating with an angular speed omega and acceleration alpha, is now affected by linear acceleration A is equal to R alpha and angular acceleration about O. Now the second phenomenon is moving forward. That is when P, a horizontal force which is acting tangential to the wheel, causes the wheel to move forward. Now, since the wheel is touching the ground, the major frictional force is acting to resist slipping on the surface. Since frictional force is unknown, the moment about C is considered first. For this, you have to first draw the free body diagram. This is the free body diagram of a rolling wheel. So the wheel has weight, self-weight W, acting in downward direction. So the normal reaction N caused by the ground onto the wheel is acting in upward direction, perpendicular to the ground surface. Then there is a force P acting on the wheel in the direction towards right. Then the frictional force FF acts in the direction towards left at the contact surface. Then your mr omega square, or otherwise W by G into A, is acting towards the left, and I alpha, that is the torque, acting at O. Now, in order to determine frictional force, you apply equilibrium equations on this rolling wheel. The first thing is, consider the moment about C, mc equal to 0. That means, take the moment of all the forces about this point C. So what are the forces that contribute to the movement? Is P contributes to the moment about C. W does not have any moment about C, as it is acting on the same line of action. So the distance is 0. Then you have W by G into A, which is at a perpendicular distance of R from the C moment center, also contributes to the moment. Then anyhow you have I naught alpha, where I naught is mass moment of inertia, alpha is the angular acceleration acting about O. So when you take the moment here about C, frictional force and normal reaction also does not contribute to the movement about C. So let's start taking the moments, that is P multiplied by 2R, because it is the diameter, about C. That moment is in clockwise. Just assume the vector head rotating about the moment center in this direction. So it's in clockwise. So sum of the clockwise movements is equal to counterclockwise movements. So if I write 2 into P into R is the moment caused by applied force P, then W does not have any role, leave it. Here W by G into A at a distance of R. Now if the arrow at is towards left, rotate the arrowhead towards the movement center, it moves in this direction. That means in counterclockwise direction. So you can either put minus or you can take it to the other side of the equation. So W by G into A into R, a counterclockwise movement. Now coming to this I naught alpha, that is mass moment of inertia into alpha in a counterclockwise direction. So that adds up to this. So put together, you have an expression for P which is equal to WR alpha by 2G plus I naught alpha by 2R. So this is this expression caused because of the movement about C. Then comes the forces in vertical direction, sigma Fy equal to 0. You have two forces, one is W and the other one is N. So you equate N equal to W. Then you have the forces in horizontal direction, that is P equal to W by G into A plus FF. So from here you can get your frictional force FF is equal to P minus W by G into A. That means the frictional force is a function of the applied force, the weight of the wheel, gravity and the acceleration acting on the body. So if the body rolls on the surface without slipping, then only the relation A is equal to R alpha holds good.